method. So here it is. It says, if f of x is a function you are attempting to find the solutions to f of x equals 0, and x sub 0, all right, or x naught, is a starting number, then here's the actual algorithm. Called a recursive definition. So what you're going to do is you're going to start at x sub 0, right? X sub 0 is a guess. All right? So you guess a number, right? Now, what will x sub 1 be according to this algorithm? So this says that the n plus 1 number is the nth number minus the function evaluated at the nth number over the derivative evaluated at the nth number. So if we want to know what the first, or we know what our guess is, right? The next one after that, this would be x sub 1, would be equal to x sub 0, that's our guess, minus f of x sub 0 over the derivative at x sub 0. So what we're going to do is take our guess minus the function at the guess over the derivative at the guess. This will give us a new number, right? Yes. Some numerical value. That'll be x sub 1. We take that answer, and to get x sub 2, we will do that x sub 1 that we just got minus the function evaluated at x sub 1 over the derivative evaluated at x sub 1. We get that answer, that's x sub 2. To get x sub 3, we do x sub 2 minus, you understand? Yeah. So Newton's method is just very tedious and mechanical. We're going to do it by hand, but we'll see why the computer is so much easier for this, right? Understand the algorithm? Now, why this algorithm? Seems like this is like a really far, crazy idea, right? But the algorithm is not that bad, actually, if you think about it. So look at this. Let me write the algorithm down here. I'm going to do it at the first point, so it might be easier to see. Okay, that's this one right here, right? Okay, so I'm going to just mess with this a little bit. Just tell me if you believe this. What am I doing? F of x naught, or f prime of x naught equals, well, let's make it negative, equals x1 minus x naught. Okay. All I did here was move the x naught to the other side, right? And then I put this on, just flipped it around. Is that right? Y'all agree with that? Yes? Okay, I'm going to multiply both sides by f prime of x naught. Y'all agree with that? Just multiplied f prime of x naught on the left and the right. Okay, let's just keep that on the board for a second. I'm going to put my graph up here. Okay, what I'm going to do here is I'm going to pick a guess right here, x naught, right? I'm going to try and convince you that this formula works, all right? Like where it comes from. Okay, I pick a guess, put it in here. What are the coordinates of this point up here? Well, no, we're not using the exact example. X naught is what I'm plugging in. What comes out? F of x naught, right? Okay. Now, what is the slope of this tangent line right there? What is the slope of that tangent line? The slope of this tangent line is f prime of x naught. Agreed? Yes? Okay. What is the equation of this black line? What is the equation of this line? The equation of that line. I'm going to get back to this. What is the equation of that block line? Well, we're going to use that formula y minus y1 equals m times x minus x1, right? That's what we use? Okay, so it'll be y minus, what's y1? F of x naught equals m, which is f prime of x naught times x minus x naught. Do you agree? Okay. My guess, this was my guess. My next point, isn't it the x-intercept of that line? How do you find x-intercepts of lines? You set the y equal to 0, don't you? Okay, so here's the equation of your line, right? The black line. Set y equal to 0, and what do you get? Set y to 0. And you get negative f of x naught equals f prime x naught is x minus x naught, right? And if I solve this for x, that will be this, right? And I'll call it x1. That'll be my next point. Now, isn't that the formula I just had on the board a second ago? So if you just move things around, you got Newton's, like if you solve this for x1, you have Newton's method. It's pretty like straightforward, but also pretty ingenious. All right, let's try something now. Example. This is exactly like the way you would see this on the test. All right? Approximate the cube root of 5 to 4 decimals. Using Newton's method. Okay, so we're stranded on a desert island. We have no technology with us except a basic 4-function calculator. All right, we can do addition, subtraction, multiplication, division. We can't do any roots, we can't do anything else, right? But the only way off the island is if we can get the cube root of 5 to the nearest. Again, the appreciation of this is the fact that it works and that a computer will do it for us. But let's see the mechanics behind it, because I think once you understand the mechanics, this is a gimme problem on a test. All right, it truly is a gimme problem, because all you have to do is follow the algorithm and you're done. All right, so I want to know what the cube root of 5 is. So I really need to set up an equation. Watch. Right? Isn't that the same thing? I could have done this. I want to know what the cube root of 5 is. Right? I want to know what that is. I would cube both sides. If I cube both sides, I get this. Now, from here, I bring the 5 over, and now I have an equation set equal to 0, don't I? And so what I'm interested in is calling this f of x. And so I'm looking for the x-intercepts of this function, right? Any x-intercepts. Got it? Now, do we have a guess as to what we think the answer is? Close to. What's the cube root of 1? Would be 1. What's the cube root of 2? Cube root of 8, I guess is what I'm getting at. Would be 2. So it's probably between 1 and 2, isn't it? I hope that you can look at this and realize that the cube root of 5 is somewhere between 1 and 2. Yes? So why don't we guess with 2? So I'm going to let my guess be x naught equals 2. Now the computer A computer would use a guess, and it really wouldn't matter how close it was, because it will converge over to the answer so quickly that it doesn't mind doing, 1,000 iterations if it has to. The computer will do it like that. So it can guess like 1,000,000, and it'll march its way down to the answer. All right, so what now? Calculate x sub 1, right? So I need to calculate x sub 1, and the formula is x naught, what is it? Minus f of x naught over f prime of x naught, which for us is really 2 minus f of 2 over f prime of 2. And as a reminder, what is f? What is the f function we're dealing with here? X cubed minus 5. And what is the derivative of this? Because we need it. 3x squared. Right? We are calling the left side of this equation f. All right, so let's continue this computation. This is 2 minus, what's f of 2? So we get to plug 2 into this function. 8 minus 5 is 3 over, now we get to plug 2 into this, so 12. So we get 2 minus a fourth, which is 1.75? $1.75. With me? Now we do x sub 2. X sub 2 is x sub 1 minus f of x sub 1 over f prime of x sub 1, which is, what is x sub 1? 1.75 minus f of 1.75 over f prime of 1.75, which equals, now we need our calculator, our four-function calculator. Because I need to do 1.75 times 1.75 times 1.75 minus 5, or cube it, right? So 1.75 cubed minus 5. With me? So I have 1.75, that's this, minus this. I just calculated on my calculator, I got 0.359375 over, now I need to plug 1.75 into this. Square it and then multiply it times 3. So I get 9.1875. Then I do division. So I have 1.75 minus 0.0391156. My calculator keeps going, but we want this to the nearest 4 decimals, right? So I'm going to go out like, let's see, here's 1, 2, 3, 4, 5, 6. I'm going out 7 decimals here so I can be safe. All right, so do this minus this. $1.71,088,44. And that's now my second, well, this is actually my third number. This is my starting number. The first one we calculated, this is the second one we calculated, right? It's 1.71,088,44. And now x sub 3. When am I going to stop? When do I actually stop? Well, let's do x sub 3 first. 1.71,088,44. That's the second number. Minus f evaluated at 1.71,088,44 over the derivative evaluated at 1.7108844. Y'all get the idea here? Do y'all agree that this is straightforward? As long as no? Is it or not? You have to let me know. Does it not seem straightforward? Do you know what I'm doing? Why don't you ask me? Come on, ask.
We keep doing this until...
Okay, yeah, so when do we stop?
So after the first 4 decimals stop changing?
Yep. So look at this first answer we had, right? Well, our first answer is 2.0000. I'm looking at the first, let's look at the first 5, okay? This is my answer, 2. So after the first iteration, it changed a lot, right? It changed from a 2 to a 1, then I have 0.75, it was 000. So the first 4 digits here, right, are 7500. Now, when I did it again, now I have the 1 is still the same, right? So 1, 1. Now, looking here at these 4, right, I have 7108. Very different than 7500. Next one, we'll see, right? And what I'm looking for is when those first 4 stop changing. Okay? Now, it may seem like we're going to be here forever, but I'm pretty sure it's going to converge pretty fast. Does that clarify what we're doing? As far as the algorithm, are y'all clear on that? Okay. Yeah, we get to plug that in. That sucks. This would be really nice. Like, wouldn't this be good? Like, if you could just write a program to do this for you? That's the whole point. Okay, the whole point of this is the way a computer does this. It is a program that is written. You type in, solve this. It does this algorithm. Boom. It spits out the answer. All right. But you can see the usefulness of it. I think. Maybe not. All right, so I'm gonna plug in 1.71, that thing, 1.7108844, and I'm going to cube it.
I feel like it kind of gives us appreciation for a calculator.
Yep. It gives you appreciation for the calculator and how humans have used their minds to solve problems. You know, you can't use a computer to solve a problem like this without understanding the theory behind it, right? Like Newton had to understand how he could use that tangent line to get solutions. Once you have that connection, then you can do a lot of really great things. Okay, so I got this. I've got 1.7108844. I'm going to subtract from that. I plugged into the top there 0.0079732. That's good enough. Over. Now I need to plug that 1.7108844, square it, multiply times 3. I'm getting 8.781376, something like that. Now some division there. And I will subtract it from that over there. I get 1.709976, something like that. Anyone else get something like that?
Yeah, I got that.
Okay. So now let's look at our first 4. 7099. Over here we are at 7108. Okay. Shall we do another iteration? Okay. Now, you get the idea, right? Okay, let me come back up here. I'm pretty sure I wrote the program to do it here. Yeah. Okay, let me see if we get the same things here. So there's the code for it. It's pretty simple. It's just a do loop. That's all it is. I'm going to erase this. I'm using some built-in functions with this program. So this is like C++. It's like a C+ based language, but it's got a lot of built-in functions. So I get to cheat a little bit. So let me change this because I had not. This was okay. This was -5. Oh no, cubed -5. There we go. Oh, and my guess, hold on, my guess was not 7. My guess was 2. Whoa. Something ain't right. No. No, my guess. Oh, my guess is this one, not that one. Sorry. There we go. That's it. Can you all see it? So we had 1.75. The next one was 1. Was this right? 1.710, and I rounded, or no? Was it 88? Yeah. It was 88. And the next one is 7099. Yeah. The next one is 7099. The next one is 7099. Oh wow! So we would have got it on the next one. Wow. I got a little lazy, but it would have been the next one. You see that? So that's the way it's done. And look at these. I don't know if I make this bigger if the answers get bigger. Let me see. Yeah. Yeah. So look at this. I always want to erase those stupid dots.
How did they get there?
I don't know. I don't know. Okay, so look, let's see where they stop changing. Let's see. 7s are the same. 5s. So they were good up to here. These 2 are good. Whoa. 6 up to here. And then 6, 9. Right here. And then they're identical. So when we talk about how fast Newton's method converges, look at that. After 1, 2, 3, 4, 5, 6, after 7 iterations of this, you know what the cube root of 5 is? Out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10, 20, 30, about 40 digits. You can go about 40 digits out on the cube root of 5 by 7 iterations of this. Yes?
Is that like a rate? Like that's going to always be constant for any root or any cube root?
Well, Newton's method works for a lot of functions, but there are functions that Newton's method will go crazy on. Like if you get it, if you can do it appropriately, you can have that tangent line start doing crazy stuff. I don't know, I just think of like some crazy sine function. Like I need an X-intercept. Okay, so let's say we're going after that X-intercept. So you take a guess, right? And it comes up here, and then it drops your tangent line down. And then you come back up, and now the tangent line drops you back down over here. You see? And then you start, right? So what your calculator does is a combination of that bisection method. So what it does is it goes and it tests 2 points. It looks for a sign change, right? And then it starts to come down, and it says, okay, now I'm in here. And then for that final part, like here, you'll just start to down. So you have Newton's method. What a computer does is like a combination of all these efficient methods. And there's other methods. These aren't the only ones. There's other ones. So, but this helps you appreciate how quickly it converges down, right? Bisection method, I can't imagine, but every time you cut an interval in half, think about how small an interval gets if you cut it in half. What does it take to move over 1 decimal place? You have to cut it down by 1/10, right? So each bisection method, you would almost need like 5 bisections to move over 1 decimal place. And if we're going 40 decimal places, you know, like 200 iterations to get to the same precision. All right, what do y'all think of that? You think you can handle that? So let me give you another one real quick. Just so you can see it. We have what? How many minutes? Okay. Solve cosine x equals x. Let's do this to 4 decimal places, okay? Solve this to 4 decimal places. Now, you cannot solve this by hand. There's no way algebraically to solve for x. So we're going to try Newton's method. But we first need to make it what? Before we can do Newton's method, we have to do what? Set it to 0. So we're going to set it to 0. We're going to write cosine x minus x equals 0. And the left side of this, we're going to call our f of x, right? So f of x is cosine x minus x. And the derivative of that I will need is negative sine x plus 1, right? What now? I need a guess. Well, it might help us if we graph. Just mentally graph. This is cosine, and this is x, right? We know this right here is what? Pi over 2. Pi over 2, which is a little bigger than 1, right? So maybe we start at 1. What do you say? Start at 1? Just see what happens? Yes?
Shouldn't that be a negative 1? Or minus 1?
Oh, you should be minus 1. Yeah, thank you. Don't know why I put my plus 1 there. All right, so our first guess is x sub 0 equals 1. That's our guess. X sub 1 equals 1 minus f of 1 over f prime of 1. That's always the easiest one to do, right? Because they're all nice, they're nice integers. From here on out, it's going to suck because we're going to have to. Now, look, we're using our calculator to get cosine and sine, right? It's kind of cheating because if we could do that, then we could probably solve this with a calculator anyway, right? But again, make sure you are in what mode? Radian mode on your calculator, yes. And so I'm going to be doing, just for clarification, this is going to be 1 minus what? Cosine of 1 minus 1 over negative sine of 1 minus 1. Yes? That's what I'm doing? Does anybody have a result for this entire chunk right here? Not yet. I'm getting 0.249636132. Anyone else get something like that? Yes? Did I go too quick there, or could you all plug this in? Anybody else get this? Oh, you're still working? Okay.
I got 57.2.
Something's off there. I think your parentheses, got to make sure.
Radius? I mean, radius.
I got 0.75. 0.36.
All right, let me go a little different. Cosine 1 minus 1. The top is negative 0.459697. That's the top. The bottom is negative sine of 1 minus 1. The bottom is negative 1.84147, something like that. And then when you take those ratios, you get this, and then you're doing 1 minus that. So 1 minus that is, you get 0.7503638, blah, blah, blah. And you know what to do with that now, right? You plug that in, you do the next one, which I'll have the computer do. So I'm going to go back up to this thing. I'm going to edit my code real quick here. We were trying to solve cosine x minus x, right? And our guess to start was 1. We had 0.7503638, right? The next one changed. So it took 1 iteration, 2 iterations, 3. On the 4th one, you're going to have it, right? So it's going to take 4 iterations for you to see that there's no change in these first 4. And man, this one converges even faster. Look at this. On the 5th iteration, from then on, the first 40 digits don't. Remember I was counting 10, 20, 30? I could have just looked here. This says how many.
You just have so much in your brain.
Let's see here. Curious here. So the last two are identical.
60 digits out.
60 digits out
On the 7th.
on the 7th iteration. Let's do 20 iterations, and let's go 160 decimal places. It's not going to fit on the screen. Let me see. I'm going to shrink it down here. Hold on. Yeah, but we can look at this. Let's see. And let's go.
The last.
These two. Look at these. These are already there. Look. So how many iterations was that? That's 1, 2, 3, 4, 5, 6, 7. On the 7th iteration of Newton's method, we have the solution out 160 decimal places. That's impressive, right? Are we done? All right. So the test. I was thinking about the test and what's going to be on it and stuff. Let's just briefly talk about it. Your homework, right? That's what you're going to study? Yes. So we are going to be doing derivatives of logs and exponential functions, right? Derivatives of logs and exponentials. 3. That's 3. Okay, so in 3, all you need to know is the formulas, right? And they're on your formula sheet, which you can bring. Okay? So derivatives of exponentials and logs, just remember how to use chain rule with them. And then we move on to the next one with 3, right? Derivatives of inverse trig. Those formulas are, no, we didn't do that? Okay, well, you don't need it anyway. 3, 7, the formulas are on your sheet, but like arctangent x, we just did the derivative a little while ago, right? I wouldn't ask you anything more than a simple derivative. Don't worry about 3, 5. 3, 7, L'Hopital. L'Hopital's big section. So I would anticipate a majority of this test, I'd say 40% of this test, 40 to 50% is this section right here. L'Hopital, because in L'Hopital, where was logarithmic differentiation? Hold on.
It starts in
Was that 3? Hold on. Where was the logarithmic differentiation? Thought we had that.
3, 4, 1.
Hold on. Where was that? Oh, it was in 3. It was in 3. Yep, that's what I thought. I'm like, where is it? So we do L'Hopital's rule, and then at the end of that section, we start taking derivatives of things that were weird that we had never seen before, like the function x to the x. Like, what's the derivative of this? And we had to do logarithmic differentiation. So that's section 3. 50% of the test, easily 50%, is knowing how to employ L'Hopital's rule on limits, but then also that entire topic on logarithmic differentiation is in there also. So please look at it kind of as two different things. And those were in your homework problems, so follow those homeworks and you should be okay.
Inverse trig function?
No, we're not worrying about that. So 4.1 is finding the maximum minimum values of a function on a closed interval. So that was that closed interval method, give you a continuous function on an interval. You find the critical numbers, you plug in those and the endpoints into the original function. You compare, biggest is your max, smallest is your min.
Oh.
Okay, that's on there. And then 4.2 is mean value theorem, and that's where I give you a function and I ask you to verify the mean value theorem. So you have to find where the slope of the tangent line is equal to the slope of the secant line. And in the homework you had to do this, like find the value of C such that blah, blah, blah. So you'll have something like one of those. And then the last topic is what we were just doing with increasing and decreasing concave up, concave down. Does that seem, I mean, I can envision the test being, the first few problems being like find the derivative, right, with logs and exponentials. And then the second part of the test being find the limit, right? L'Hopital's rule. And remember, we have all these different forms. We have, 0 over 0, infinity over infinity, that's the clean form, right? Just do derivative top and bottom. Then you had like 0 times infinity. That's where you had to take 1 and drop 1. And then you had like 1 to the infinity or something like that, where you had to log both sides, drop the power out front, do whatever you need to do. Those were harder. And then you have the logarithmic differentiation, which is a different topic. So you have, the test would then switch from find the limit to find the derivatives. Find derivative, and you would use logarithmic differentiation. And then find max min, closed interval, verify mean value theorem, concave up, concave down, increase, decrease. I mean, that's it. That's the test. Oh, Newton's method. Okay? So one of these. On this Newton's method, if I ask you to do it, I'll have it happen within the first 3 iterations. Okay, so I'm going to want you to iterate it, but if it's like not changing after like 4, something's wrong with you. I mean, with your calculations. Okay. All right, does that sound like, I mean, is that good enough as far as a kind of snapshot of what the test is going to be like? I don't know. Bonus? I'll make the test and then I'll find out how long it is, and maybe I'll move Newton's to a bonus. I don't know. We'll see. Yeah. So the bonus is Newton's method down. You have to do 20 iterations.